Okay, welcome, wonderful people. This is Mr. Ndabezita once again, and we are looking at our second tutorial in mathematics. So remember, these tutorials are done for somebody very important. Well, this is the slide that I have as the opening slide, and there's a lot of confusion as you can see here, but everything will become very clear as I explain. So we have this example one. Let's verify the natural domains and associated ranges of some simple functions. The domain in each case are the values of x for which the formula makes sense. So in the previous tutorial, we spoke about a function. And we said this is the machine where we plug in the values of x to find the corresponding values of y. And it has been said that the graph of y equals x squared, the function that happens between y and x squared, it's in this format. And the domain, which are the values of x that satisfies a given conditions, are from negative infinity to positive infinity, and the range is that way. So I thought to myself, okay, Ndabezita, in order for people to understand what is happening here, let me draw this graph so that when we explain what is happening here, there would be a graphical explanation of that. So we have the graph of y equals x squared, and I've drawn the graph for the values of x from -1, 0 to 1. So I'm moving from the left to the right, because based on the number line on the x-axis, remember, this will be -1, 0, and 1, 2, 3, and so on. So I plug in the values of x in this machine, which we call a function, in order to find the corresponding values of y. So where I see x, I put -1, and -1 squared, it's 1. So when x is -1, the corresponding y value is 1. So I've tried to show that in here. And then secondly, when the value of x is 0, 0 squared is 0, the value of y is 0. So there's a relationship that is happening here. For each value of x, we have a corresponding value of y. And I tried to demonstrate that here. And then I drew up a Cartesian plane where I have the intervals on my x-axis. I check, I have -1, 0, and 1, so I can use the interval on the x-axis of 1, 2, 3, -1, 2, 3, and so on. Remember, from 0 going to the right, x is positive. From 0 going to the left, x is negative. Hence, I have the negative values there. And from 0 going up, the values of y are positive. 0 going down, the values of y are negative. Okay, that is fine. Nothing mysterious about this. So what I just simply did was to just take the values of x where x is -1, because remember, this is a relationship, a coordinate. When x is -1, y is 1, there it is. Therefore, you make your point, the very first point, there it is. When x is 0, y is 0, that is the origin where both x and y are 0. And when x is 1, y is 1. So when x is 1, y is 1, they are the points. And this is a parabola. So I try to join these points just to show you the continuity of the graph. So the graph keeps on going upwards. So this arrowhead shows that it goes to the values of y that we do not know, because it keeps on continuing and so on and so on. So what will be the domain? The domain are the values of x that satisfies this function that we have. We can see that looking at the values of x, our graph can go from -1. We can choose a value. This is just, we just restricted ourselves with the values of x beginning from -1, but we can also have -2, -3, -4, and -5, and the graph will continue in that format. Hence we are saying here negative infinity. That is to say, not only at -1 does our graph begin, our graph can continue even if we have -2, -3, and so on. to a point that we do not know. So to that point that we do not know, we say that's negative infinity. Just from 0 going to negative infinity. But we also have to counter for this part. And we are saying from positive infinity again. Not only at 1 will our graph stop, the graph will also continue at 2 and 3 and 4 and so on, to a point, a value that we do not know. So we are therefore saying the domain is from negative infinity is to positive infinity. That's how Thomas got to find that interval. Very important. And then the range of the graph, which are the values of y that corresponds to the very values of x. We can see based on the graphical representation that our graph starts from 0 and it goes upwards. It can never go downwards based on the information that we have here, because we are squaring every negative number, and every negative number squared is positive. Even if you can increase the values here, the interval, to include -2, -3 and -4 and so on, it will never and ever go down, because any number negative squared is a positive number. So it will always begin at 0. This is what we have, going to positive infinity to the values of y that we do not know. So this will be the range of the graph. Very important that you understand that. So that gets rid of the first problem that we have. Of course, Thomas is going to explain this, but we are just trying to explain it before he even does. So we can go to the second graph, y equals 1 over x squared. And I spoke about this graph in the first tutorial. And where is this graph? I tried to draw up the graph here. And as you can see, y equals 1 divided by x, and I chose an interval from -1 to 0, from -1 to 1. We spoke about the interval in the first tutorial, so please go and refer. So right, we have the interval here, it is, we have the machine, the function, there it is, and we input the first value of x, so we will have 1 divided by -1, which is -1, that is the corresponding value of y, there it is. And then when I try to input 0 here, you have a problem. 1 divided by 0 is undefined, it's maths error, it's something else. So in the place of y, I wrote an error. So we don't have any corresponding value of y. So because there's no relationship between x and y at the point is when x is 0, so we cannot plot anything. We cannot have a relationship at that point. Why? Because for the value of the input, we cannot find the value of the output. So you just leave that as it is. And then when x is 1, the value of y is also 1. So there's a relationship there. So how do we draw up such a graph? So we have the points here, they are exactly, and I've represented the error here with a question mark. So when x is -1, y is 1. So there it is, when x is -1, y is 1. I have my first point. I cannot have this point because I don't have the corresponding y value. I skip this one, and then when x is 1, y is also 1. There it is. When x is 1, y is 1. And then, okay, one thing I need to know is that this represents a hyperbola. It's a hyperbolic graph, and you know that when the value of a, which is the numerator, when that value is positive, it will be on the first quadrant and also on the third quadrant. And this will be the shape of the hyperbola, the hyperbolic function. And then this will be the shape. So we are simply just saying the y-axis will become the vertical asymptote of the graph, and the x-axis becomes the horizontal asymptote. So very important, an asymptote is a line that the graph will approach but never touch. Hence you can see that they are not touching one another. This is the fundamental rule. It will approach x but never touch. It will approach y but never touch. So this is just an illustration of what is happening in here. Be that as it may, we were able to understand. So sorry, the domain of the graph, as you can see, values of x are moving from negative infinity. Remember, we are looking at x here, going to negative infinity. There it is. Negative infinity are the values of x moving from negative infinity and coming closer to 0. So we have an open interval there. It will approach 0 but never touch. Hence we are having this open bracket. Very important. The union sign, we are combining two things because there are two pieces here. So this is the first piece. Negative infinity is to 0, but 0 is not included because it cannot have a value at 0 because it has an asymptote at that point. And then secondly, we are on this graph. The values of x are moving from 0. They are moving from 0. Remember the value of y here. I wish I had a pointer. Let me just try to look for something that might allow me to point. Okay, can I just say allow editing if it's possible? Okay, let me just leave it. Okay, that's fine. So remember, we chose the value of x as 1 here. We can choose 0 0.5, 0 0.4, 0 point something until we get to 0 here. Hence, we are saying the union of 0, but 0, x is not defined at 0 because we have an asymptote there. So from 0 is to positive infinity. There it is going. The graph is going towards positive infinity in that direction because we don't know what value, the last value of x. As much as we don't know the last negative value of x, we also do not know the last negative positive value of x. Hence we are saying to positive infinity, and we are making that open bracket because we don't know what the last value would be. So that takes care of the first and the second one. Let's go to the second slide. Let me just take you through that. The graph of the square root of x. So do I have the graph of the square root of x? I tried to have it in here, as you can see. And then I drew up a table of relationship of values. -1, 0, and 1. I'm using the same interval for x. So you would go and substitute the value of x. You would have the square root of -1, which is an error. And then we don't have a value of y when x is -1. The square root of 0 is 0. So when x is 0, y is 0. We can plot those to that 1 point. And when y is 1, the square root of 1 is 1. There we have it. And then we can try to draw up this graph. We do not have this. So 0 is to 0, there it is. 1 is to 1, there it is. 2 is to 2, 3 is to 3, and so on. So you get a graph of this particular shape. So that is the graph of y equals the square root of x when x is greater or equals to 0. The only positive side of this. Because we cannot have for any negative number. Remember, even if we can have -2, it will keep on saying error, error, -2, -100. So you cannot have anything on the side. Very important that you see that, because the square root of a negative number is a complex number. So you will not have anything there. So this would be the shape of the graph. Now let's go back to Thomas. And then he tells us the domain is 0 is to positive infinity. Let's check. It is true. There it is. Now, I want you to notice something here. And we have an inclusive bracket. Why? Because it is defined at 0. There it is. We have a point at 0. Therefore, it is defined at 0. Therefore, we will have a square bracket. Remember, we are speaking about domain, the values of x. There it is. It is continuing in that direction, heading for values that we cannot even tell. So we say that it is positive infinity, and because we don't know what value that last value would be, we are using an open bracket here. Very, very important that we have an open bracket. It's very important that you understand the difference between the two. All right, that is fine. Let's go and check the range of this function. You can see that the range starts at 0, so 0 is defined at that point, y is defined at that point, and it keeps on going up for values of x and so on, heading towards positive infinity. Very, very important. And then we have the other graph. I tried to draw up the graph. Let me see. There it is. The graph of the square root of 4 minus x squared. I have a table of values. There we have it. The square root of 5, 2, and the square root of 3. So I would substitute these values in the equation. The square root of 4 minus into, please be careful here, you need to insert your x into the brackets because a negative has to multiply that number. So 4 minus into minus 1 will give you a positive, the square root of 5, and then when x is 0, and you will have the square root of 4 minus 0, which is the square root of 4, which is 2, and then when the value of x is 1, 4 minus 1, the square root of 3. So we will compile a table in that form. When x is minus 1, y is the square root of 5, which is the equivalency of 2 point something. There it is. When x is 0, y is 2. There it is. And then when x is 1, y is the square root of 3, which is something just below the number 2. So when we draw this, we get a shape of this nature. I know I'm not very perfect in drawing, but something of this nature you will have. So let's see the domain and the range of that function. So he says the domain is from negative infinity is to 4. So let's check. So remember, the domain are the values of x. From negative infinity, we can see that it is heading to negative infinity and so on. Negative infinity is to 4. But is the graph defined at 4? Let's check. Yes, 4 is inclusive because you would come here and say 4 minus x is greater or equals to 0. Therefore, you would take this one to the other side. Remember, you will say 4 minus x is greater or equals to 0. Therefore, you'll have x should be less or equals to 4. So 4 is inclusive. Hence, we are saying in here that the value of 4 is inclusive. The graph is defined at x equals 4. Very, very important. Just that you cannot see that in here because I did not incorporate the interval where I have a value of x as being equals to 4. Very, very important. So at 4, exactly at 4, we will have a value of y as 0 because that would be an x-intercept. Very important. So that would be the domain of the graph. And then let's go and check on the range. And the range would be 0 included is to positive infinity. Let's check. The graph is defined at 0, yes, because remember we are speaking about the range, and we said the graph is defined at 4 for the domain. So when x is 4, y is 0. So the interval of the graph is moving from 0, 0 is included, heading towards positive infinity. So I am including the value of 1 and so on and so on and so on. All these values are included there from 0 to positive infinity, and 0 is inclusive because the graph is defined on the domain at x equals 4. The value of y is 0. So the range would be 0 to positive infinity, and then we have that. And then lastly, we have this graph, the square root of 1 minus x squared. And let me check if I have done that. Here it is. The square root of 1 minus x squared. And what is it that we have in here? Okay, we substitute the values. 1 minus into minus 1 squared, we get 0. When x is minus 1, y is 0, 0, 1, 1, and 0 I have shown up here. And then what type of a graph do we get? This is the type of the graph that we get. And as you can see, pretty much that the domain is that, and the range, the domain it's -1:1, and they are inclusive because the graph is defined at -1. So meaning when x is -1, y is 0. When x is 1, y is also 0. So the domain, the range of the graph would be 0:1, 1 included. But let's go to Thomas and check. So Thomas has this, the domain s -1:1, and they are included. This is exactly what we have said. And Thomas also tells us that the range is from 0:1, and they are both included. So 0:1, and they are both included because the graph is defined at y equals to 1, and it can never go up or down. Hence we are closing with 0 and 1. Very important that we understand the fundamentals of the great Thomas. Okay, now let me just go and read for you some of the most important things, the solutions that he provides for us in text form. The formula y equals x squared gives a real y value. Remember, these are real numbers because they are the numbers on the number system. They are the numbers that we can plot. Therefore, we don't have a problem with that. So the formula y equals x squared gives a real y value for any real number. This is in the case of a parabola. We will always get a positive number, and I try to explain that. So the domain is negative infinities to infinity. We saw that, and the range is that. We also saw that because the square of any real number is non-negative, and every non-negative number y is the square of its own square root. Very important for y is greater or equals to 0. This is just to say for values that are 0 and positive. Values that are positive, 0 and positive values. All right, the formula y equals 1/x gives a real y value for every x except at x equals 0. We saw that. For consistency in the rules of arithmetic, we cannot divide any number by 0. The rules of arithmetic, Thomas is being very careful here because he knows that in the world of complex numbers, we are speaking something different. The range y equals 1/x. The set of reciprocals of all non-zero real numbers is the set of all non-zero real numbers, since y equals 1/f divided by y. That is for y is not equals to 0. The number x equals 1/y is the input assigned to the output value of y. Very correct. The formula y equals the square root of x gives a real y value only if the values of x are positive, and this is exactly what we saw. I've explained that. The range of y equals the square root of x is 0 to positive infinity because every non-negative number is some number's square root, namely it is the square root of its own square. Okay, in y equals the square root of 4 minus x, the quantity 4 minus x cannot be negative. That is, 4 minus x is greater or equals to 0. I spoke about this. Or x should be less or equals to 4. So x is defined at 4. Hence, we are saying the range is from 0 going upwards. The formula gives a real y value for all x is less or equals to 4. And immediately when you try to find the values that are outside this boundary, you will get problems. The range of the square root of 4 minus x is 0 inclusive is to positive infinity open bracket. The set of all non-negative numbers. Okay. So that was Thomas explaining to us exactly what is happening. The formula y is equals to the square root of 1 minus x squared gives the real y values for every x in the closed interval from -1 to 1. I've explained. Outside this domain, 1 minus x squared is negative and its square root is not a real number. The value of 1 minus x squared vary from 0 to 1 on the given domain. This is true. It varies from 0 to 1. from -1 to 0 the values of the domain. So any number you can get from -1 to 0 will satisfy the conditions. All right, that is that, and then we will look at the graphs of functions. So it is very important that we note that. So the graph of a function, if f is a function with the domain D, now that we understand, its graph consists of the points in the Cartesian plane whose coordinates are the input-output pairs of f. We saw that in the set notation, the graph is x such that f at x in the domain of x is an element of real numbers. So we have the input into a function, and then what is it that we are inputting? We are inputting the elements of x, which are the domain. We are inputting an interval of x values inside of a machine. If f is a function with the domain D, its graph consists of the points in the Cartesian plane whose coordinates are the input-output pairs of f. Input-output pairs of f. Okay, that's fine. The graph of the function f at x equals x plus 2, which is a straight line, is a set of points with the coordinates x and y, for which y equals x plus 2. Okay, that's fine. Its graph is the straight line sketched in that figure. That is fine. The graph of the function f is a useful picture of the behavior. If the coordinate is a point on the graph, then y is equals to the function when x is the input. Is the height of the graph above or below the point x? The height may be positive or negative depending on the sign of that. Okay, that is fine. And then here we are. The graph of f at x equals x plus 2 is the set of points x and y for which y has the value x plus 2. This is true. We have the input values, we have the machine that gives us the output values. And remember, the equation is y equals x plus 2. So we have that, and then when we plot those points, we will get a straight line in that format. Okay, that is fine. In figure 1.4, if x and y a coordinate lies in the graph of f, then the value of y equals f at x is the height of the graph above the point x or below x if f at x is negative. So this is just an explanation. Right, the value of x when it is positive, the value of y is above, as you can see, and when the value of x is becoming higher and higher, the value of y is below. So they are just saying f at x is the height of the graph above the point x so they are just saying the height of the graph above the point x for below x if f at x is negative. So if f at x, the value of y, for example here, if the value of y is negative, then the value of x is there, and if the value of y is positive, the values of x are just there. So this is just an explanation that is worthy of noting. All right, so we can continue in this. I think we were just trying to explain that. So by just looking at the relationship here, let me draw up your relationship into this kind of a graphical representation. When the value of x is at minimum, when the value of x is smaller, we get a corresponding high value of y. And as you keep on decreasing the value of x, as you keep on increasing the value of x, the height decreases. This is very important. When the value of x, when the x value, the x value that you are inputting on the function, when the value of x is small, we have a very high height, and when the value of x is bigger, the height keeps on decreasing. For example, maybe the value, let's say the value there, it's a 3, just for argument's sake. The height is at 0. And when you increase the value of x and maybe make it 4, the height begins to be negative. The values of y are negative. So this is the relationship. For a value of x that is smaller, you get a higher height, and as you increase the values of x, the height also decreases. Very, very important. An increase in the input result in a decrease in the height. So the higher the value of the input, the smaller the value of your height. This is the relationship that we can see happening here. On the other side, there's another relationship happening here. When the value of x is 0, the corresponding y value is 0. As you increase the values of x, the values of y also increases. As you can see, when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. When x is 4, y is 4, and so on. This is a parabola. But let's look in here. When the value of x is 0, y is 0, because 0 squared is 0. When it's 1, it's 1. And when the value of x is now 3.5, we have 9.25. When x is 2, the value of y is 4. So the relationship that is happening between x and y, as you increase the values of x that are bigger as you go to the right, therefore we expect higher values of y. On the other hand, when you decrease the values of x as you go to the left, and the graph will also go in that value. So when the values of the interval here, the values of x are negative, the graph, the values of y keeps on rising and rising and rising. Very important. So one point that is worthy of noting is that for the values of x that are different, for example, for -1, you can see the corresponding value is 1, and for -2, we can get a value if we plug it there, which is 4. So irrespective of the value that you input, you will always get a y value that is positive. Why? Because a negative number squared will always bring out a positive value. Okay, that is fine. And then we can represent a function numerically. Remember, there are 4 ways to represent a function. We can represent a function as an equation. This represents a function as an equation. Very important that we understand that. And here we are representing the function in a graphical representation. The second way of representing a function, very important. So we are still dealing with representing a function in a graphical way, and so on and so on. And then we have another way, which we said we can represent a function numerically. So right, so we have seen how a function may be represented graphically, that is true, by a formula, the area function, and so on, and visually by a graph, just as we saw. Another way of representing a function is numerically. So this is the third way. Through a table of values, numerical values. So here, I was in fact trying to show you the numerical way of representing a function. All right. Through a table of values, numerical representation are often used by engineers and experimental scientists for their usefulness, of course. from an appropriate table of values. A graph of the function can be obtained using the methods illustrated there. That is true, possibly with the aid of a computer. We have computer calculators that we use every time in order to get this representation of a graph having the numerical values. The graph consists of only the points in the table called a scatter plot. For example, there. All right, musical notes are pressure waves. Okay, we are not interested in that. So this is just something, guys, that I wanted to share with you so that you understand moving forward from here exactly what a function is, how do we make sense of the function, the different ways of representing a function, making sense of the domain and the range of a function. So thanks a lot for looking into this tutorial. This is Mr. Ndabezitha, and I will see you in the next tutorial.